No. Okay. Set it up. Oh, Walters, you're on time. So okay, join. I see. Yeah, very also. Hello? Not yet. Canterbury's on. Ah, okay.
Hello.
Hi.
Hello.
Hello.
You still sleepy, Ryan?
Yeah, I'm always sleepy, but
You
I'm used to
gotta get more sleep, guy. You got too much going on?
Yeah, and I'm a little bit of a night owl.
Oh.
Yeah.
So you
I
like-
take naps during the day, so it's all good.
I see. Okay. Walter said he might be either a little late or a little have to leave a little early because he has to help judge a middle school science contest. So that's his story. And Logan, I'm having trouble getting work from you, guy. What's the story?
I am.
Did you see my corrections? Or I sent in my.
Yes, I saw the email that you sent.
Okay. Did you?
I didn't look at it yet because it just came.
Okay. Great. Because I think my definitions are better now.
Good. Good. I'll get that back to you later today.
Okay.
Oh, I am. Let me send this again.
Okay. Okay. And those two back ones, I never got those, so those are
Yeah.
history. Okay. All right, we're gonna start because Walter said that he might be late. So, okay, you can send them after class is okay, Logan, but just right away.
Yeah, I was about to send it off like right now.
Okay, fair enough. Try to get it in before class if you could.
Yeah.
Okay.
I'm sorry.
Okay. All right. I know you have one heavy schedule. I don't know how you do it. To tell you the truth. Okay. So the story today is we're going to go over a lot of things, and then the homework for and you guys have to make, if you haven't made an appointment yet to take test one, you need to do that. That's important with your tech person, who is Steve, right?
Yes.
Steve Orr, Mr. Orr, I should say. Sorry, I'm used to calling him Steve. Mr. Orr. And so the homework is going to be, I'll post this, but just submit your weekly journal, take test one, revise and resubmit. We're going to go over the symmetry definitions and proofs in light of class discussion, so you'll have to resubmit that. and then just review for test one. That's it. So you'll have a chance to really get solid on what we've done so far. I'm going to go over all the stuff. So I'm going to share my screen. So you guys need to open Adobe Connect Tuesday. And now I realize it's a two-step process. So first I share my screen and it loads Connect. And then once Adobe Connect is loaded, I have to share my screen again. And then it says main display. And I say share. Okay. Mr. Gleason probably told me that, but it escaped me until the last few times. That's why I kept getting to, the infinite regression of screens. All right, so that's the plan. You don't need that because I have that printed. Well, I'll just minimize this guy. So the first thing we are going to do is this. I'm going to go to GeoGebra here. And I made this sketch. Can you see it?
Yes. Yeah.
And the title is Two Reflection Angle Choice. So this is a subtlety that we had not talked about, and I want to talk about it. It's also a good review. So the original figure is orange, usual colors, okay? And we're reflecting that figure across line A, which is now down here. These labels don't go very far, and you never know which end they're on. But that's line A. Okay, it's either here or here, and you never know. It's the software's choice. So A is here. This is line A. So we're reflecting the original across line A to get this red one, and then we're going to reflect the red one across line B, who is up here, to get the. I probably should have colored them, but that's all right. To get the indigo. That's always our image. Our final image is indigo. So those two, the composition of those two in that order, first A then B, is a what? Remember? So we're ignoring the red one.
It's a rotation, right?
Yes, it is. It's a rotation. And what's the angle of the rotation?
180 degrees.
It looks like it because, so I'm going to move the lines. And Logan, I want you to chime in here too. It's okay to be wrong.
It looks like
we had done this. This was one of our results, but so it was similar to two reflections. Let's go back to two reflections. You have two reflections in parallel lines. Logan, I want you to chime in here on this one, okay? Yeah. So imagine I'm holding up. Can you look at me? Two parallel lines, and we're reflecting first in one and then in the other, and that's equivalent to what?
Translation, I think.
Yes. And what's the? You have to tell me more.
It's 2x plus 2y equals the distance that it moves, right, where x is the distance between the first and y is the second.
Yeah. So.
I mean, yeah.
Yeah. So without reference to x and y, tell me it's twice what? The distance is twice what?
Twice the distance between the point and the line.
Which point?
The initial point?
No.
Line.
No, because it's always because you can move the initial point, and that's not going to change. The specifications of a transformation always involve the objects of the transformation and never the original point. Okay. That's really important. Okay, I'll say that again. The specifications for a transformation always involve the objects of the transformation, never the original point.
Yeah.
All right. So what's the distance?
It's
right?
the two lines.
So it's twice the distance between the lines, right? And what's the direction?
The same way that
describe it with reference to the lines. Ryan, Dina?
Perpendicular to the line?
Yes. Yes, perpendicular, right. So the direction is perpendicular to the lines because when we reflect, it's perpendicular, right? So the direction is perpendicular to the lines and it's twice the distance. All right. This one is similar. So it's twice something, but twice what? So it is a rotation, yes.
Is it twice the angle? It wouldn't be beta or A, but or beta or alpha, but would be twice the angle that the.
Why do you say it wouldn't be alpha or beta?
Because that would be a rotation of 180 degrees.
Well, yeah, not both of them, not alpha plus beta. That's right.
Yeah, and the.
So okay, let me stop you for a minute. The other one was twice, the translation was twice the distance between the lines, right? And this has to do with angles. Twice the. Make the lines close together. Make it smaller. Let's see. Oh, I need to move them. Let's see. I can't move everything.
Is that just twice alpha?
Yes, it's twice the angle between the lines. That's right. Twice the angle between the lines. And yes, good. And that's why I drew these. It is twice alpha, yes. But here is notice the title of this. There's two reflection angle choice, right? So what is the angle between the lines? Is it alpha or is it beta?
It's both, or it's one way, and then it's twice alpha clockwise and twice beta counterclockwise.
Yes. And how come they're the same? How come twice alpha clockwise is the same as twice beta counterclockwise?
Because they're both part of the same. I don't know how to phrase that. Because they're parts of the same whole.
Almost. Okay, so look at alpha. There's a relationship between alpha and beta. Logan, tell me the relationship between alpha and beta.
They equal 180, or they add up.
Well, let's say it better.
Make a straight line.
What do you mean by equal? They equal 180. You mean they each equal 180?
Oh no, the angle measures of B and A.
So, and what operation is that?
Addition.
Addition, that's right. They add up to 180 degrees. You got to be precise. They add up to 180 degrees, right? And now we're talking about twice.
So that's multiplication. So if you multiply 180 by 2, it's 360, right?
That's right. So the 2 alpha and 2 beta are going to add up to 360.
Mm-hmm.
So if we go around 2 alpha one way, and we go around 2 beta the other way, they're going to add up to 360. So we're going to get to the same spot.
Okay.
That's the deal. Amazing the way that works, right? So the angle between the lines, it doesn't matter which angle, as long as we're careful about the direction. And we know the direction because line A comes first. We did it first in line A. So as you said, Ryan, it's 2 alpha clockwise because we're going from here to here, or 2 beta counterclockwise. Okay, good. So that was a little fine point that I wanted, and it was good because not only did we do the fine point, but we got to review some things that are really important. Okay?
Okay.
Good. All right. So I'm going to hide this. And the next thing we want to do is, if we don't get through the 3 reflections, 6 cases, I mean, I'll try to, but I'm going to leave that till later because the other stuff is more crucial. So symmetry definitions and proofs. That's the one I want to do. We had just barely started that last time.
I felt like it took forever a minute.
All right. Put this up here. All right. And we're just going to talk about some of it. And I want to talk a little bit more about the first. So you can see my screen?
Mm-hmm. Yes.
Okay. I want to talk a little bit more about D, 1D, which was an equilateral triangle. Make a symmetry definition for an equilateral triangle. And this will be a subset of the symmetries. So I'll remind you that part C was describe all the symmetries of an equilateral triangle. Or you remind me, what were they?
You had, there's
Ryan,
there's
you
3 lines.
give me some, and then Logan will give me the rest.
Okay. For line symmetry, there's 3 going through one vertex and then to the opposite side.
Mm-hmm. What point on the opposite side, or what's the relationship?
Midpoint.
Midpoint. Okay. Good. Okay, that's good. Logan, what's the other symmetry?
I've forgotten, honestly. Yeah.
Okay. Good. Ryan, can you give him the minimal hint? The smallest hint you can give him that will get him unstuck.
A pinwheel?
There, that's a good hint.
What if you spin it?
Spin the whole thing?
The triangle.
What part of the triangle?
Like the whole triangle. Like if.
Oh, it has rotation symmetry, but
yes, it does.
Is that what you mean? Is that what you mean? Oh,
that's
okay.
Right.
I did my homework incorrectly.
All right.
I thought you meant
it has rotation symmetry, and when we say rotation symmetry, you have to tell me more.
If you rotate it, it can be rotated 3 times, I think.
Yeah, that's right. So what do you call that? Do you remember what we call that?
I just say the after image maps onto pre-image, it's
right. Okay, there's a word, and the word is confusing because it seems like it's a reflection word, but it's really a rotation word because the word it's a good F word. It's a good F word, and it means times in archaic language. So it's called threefold. Threefold meaning three times. And that means, so it's threefold rotation symmetry. Threefold rotation symmetry, and what does that mean? It means that when you, finish that sentence, when you do what?
When you
rotate it.
3 times of 360 of a circle of
Okay, close. Ryan, can you give me a better description?
You rotate it 120 degrees 3 times.
Almost. Okay, so it could be called 120-degree rotation symmetry. That's correct. But we usually call it threefold rotation symmetry because when you rotate it one complete time, so that's always one complete time, it matches with itself 3 times.
Okay.
First time at 120, the second time at 240, and the third time is one complete turn. So every figure has one fold rotation symmetry. That's not at all interesting. If you turn the figure all the way around, it matches to itself. So we never talk about one fold. That's silly. All right.
So if you're talking about a image that has like 90 degree rotational symmetry, you're talking about fourfold?
Yes. And what figure has fourfold rotation symmetry?
A square?
Yes.
Okay,
stop for a minute. Logan, can you tell me a figure that has twofold rotation symmetry, but not fourfold? So if a figure has twofold, it's going to have, no, the other way around. If like a square. If a square has fourfold, then yeah, it has twofold, right? If you rotate it 180, it would match. But that, again, is not interesting. So we always want to pick the highest number. That is the most number of times that it matches when it goes around, the highest number. So when I'm asking for a figure that has twofold rotational symmetry, I'm asking for a figure that when you rotate it 180, it matches with itself, but not. So
maybe a rhombus?
What?
A rhombus?
A rhombus.
A rhombus? Yeah.
Yes. A rhombus has twofold rotational symmetry. Good. And there are others. Okay, are we clear now on what the fold means? Putting you on the spot, I'm sorry, but it's important. And no points lost. I mean, I really appreciate your trying and saying I don't remember, and or this is because when you give me your ideas, then I know where to go. But if I don't get your ideas, I don't know. So that's really important. There's no embarrassment. And if I ever do anything to make you feel like, you're embarrassed or something, then call me on it and say, Mr. Douglas, you said you wouldn't do that. Okay, so that's really important to me. I really try hard. But sometimes I'll mess up and just say, Mr. Douglas, you said. Okay. All right. So now we're going to go to the symmetries of the special quadrilaterals. And we're just going to talk it through. I know you've done this, but I want to talk it through a little more. So, and I'll just alternate. So Ryan, you can start, and then Logan will do the next one. We'll go back and forth. So this time we're just talking about the symmetries. What symmetry? So what symmetry does a parallelogram have? Brian?
That was rotational. Would it have twofold?
Yes, it has twofold rotational symmetry. And the other thing that I didn't mention last time that's important is we're going to think about the diagonals when we talk about properties, not just, so we're going to milk it for all the properties we can do. All right? Including diagonals. So that's going to, okay, sorry, come back. Okay, Logan, what about it? Actually, you told me a kite. You told me some of it, but now this time I want all the symmetry. So you told me that a kite has twofold rotational Oh no, you didn't. That was a rhombus. So I'm sorry. So go to a kite. What kind of symmetry does a kite have?
It has reflection symmetry down the middle.
Yeah, let's be better about the middle. What's that called?
Down.
So describe the segment to me. Describe the segment that you are reflecting.
It's the perpendicular bisector of the two sides.
Right. But just in terms of a kite, don't worry about the properties. Just describe how to draw the segment. What do you do?
You draw a line from one vertex, from the top vertex to the bottom vertex?
Yeah, so from one vertex to the opposite vertex, that's right. And when you have a quadrilateral and you draw a segment, so this is really a segment from one vertex to the opposite vertex, what's that called?
A transversal?
Parallel lines, yes. So Ryan, can you give him a hint? You can give him like the first one.
A diagonal?
Yeah, it is a diagonal. That's not a hint, but yes, that's the answer.
Oh.
Okay. Okay. Sorry. So yes, it's a diagonal. So a kite has reflection symmetry across a diagonal.
Yeah.
That's enough. Okay? Across a diagonal. And yes, it's, see, it doesn't have to be, the position of the kite, who knows? It just has reflection symmetry across a diagonal. That's enough. Okay? All right. So, good. All right. Ryan, we're to you. Isosceles trapezoid.
It has it only has a single or a one-fold rotational symmetry.
Okay, so imagine this, and you're going to rotate it. Oh, it only has, you said, one fold?
Yes.
Yeah. Okay. That we don't say that. Everything has one fold, so that's not interesting.
Okay. Then it has a line of symmetry on these with the line segment from the midpoint of base 1 to base 2.
Yeah, we don't even know bases. So from the midpoint of one side to the midpoint of the other side. And then the word base comes after that, once we know. But that's the definition, right? Good. So it has one line of symmetry from the midpoint of one side to the midpoint of the other side. Excellent. Okay. Logan, you already told me something about a rhombus, so tell me, repeat that and tell me more.
It's got twofold rotation symmetry.
Good.
And it's also got two lines of symmetry.
Mm-hmm. And describe
both diagonals. And
Perfect.
It's from...
Bingo. Got it. Perfect. Yes. See, these words are useful. Yeah, Ryan.
With the isosceles trapezoid, we don't even have to say the midpoints, right? We can just say from one side to the other?
Yeah.
Okay.
Not through the vertex, right? That would be correct. Yes. From one side. Yes.
So, a rectangle has twofold rotational symmetry, and then two lines of symmetry, not through vertices.
Good. Okay. Where? Oh, wait. You did the rectangle, Ryan?
Yes.
Yeah. So Logan, do the square.
Okay. It's got fourfold rotational symmetry, either to the middle of the side or the vertex to the opposite vertex. It also has lines of symmetry on those same points.
Yeah, so how many lines of symmetry does it have?
4.
Yeah, it has 4 lines of symmetry, and 2 of them are go ahead.
2 of them are diagonals, and the other 2 are through the midpoints of the side.
Great.
To the other midpoint.
Yeah, you got it. Good. Okay, so now before I go on to number 3, I'm going to go back here to a symmetry definition for an equilateral triangle. So again, here this is a subset of the symmetries. We don't need them all, and there's more than one possibility, I think. So we said that an equilateral triangle has threefold rotational symmetry and 3 lines of symmetry. So can you think of a smaller subset that would completely determine an equilateral triangle? Either one of you.
Could we just say that it has 3 lines of symmetry through vertices?
Yeah.
Would that be better than, or that would exclude the rotational?
Well, that actually would imply the rotational. Okay. Because if you reflect once in one of the lines and then you reflect, we just did this, remember? Reflect once in one of the lines and then reflect in the other line, it's equivalent to a rotation.
Okay.
Yeah. So yes, 3 lines of symmetry. In fact, do we really need 3 lines of symmetry?
You just need 2.
Yeah. 2 would be enough.
Wait.
Okay, we're getting a lot of sound. Hi, Walter.
Yeah, hi.
We're getting a lot of sound for some reason. Maybe.
Yeah.
There. Good. Okay. So, Walter, how was your middle school science fair? Can you hear me?
Yeah. I don't think I should talk right now since I'm in a public place right now.
Oh, okay. All right. Oh, you're still there. Okay, so don't talk. Okay, just watch. Yeah. Fair enough. All right, so what we're doing is going over the symmetry definition. Yeah, you should mute your microphone, Walter.
I don't have it. It's still in the clipboard.
Walter?
It's just over there.
You mute your microphone. There you go.
Yeah.
Okay, thanks. Okay, so now we're on the symmetries of special quadrilaterals. And this, I'm sorry, we're on 3, the symmetry definitions for special quadrilaterals. All right, so this is going to be a subset, and we'll just do a few of them because I want to go on to the rest. So, let's. Yeah, I want to go to some of these that have lots of different symmetry and we don't need it all. So like a rhombus, E. So Ryan or Logan, you're going to be the ones who are talking because Walter can't do this. So for a rhombus, a subset of all the symmetries that we just said that would define a rhombus.
How about we use the how about we say that it's a quadrilateral with 2 lines of symmetries the diagonals, or using the diagonals.
Great. Quadrilateral diagonals are lines of symmetry. Perfect. Okay. A rectangle. Logan, can you think of a symmetry definition for a rectangle?
A square that only has.
Stop right there. Now, can you tell me why starting off with a square is not a good idea?
Because you'd have to define what a square is, maybe. I don't know.
Are all rectangles squares?
Yeah.
No, so a rectangle is not a type of square. So you don't want to start off with square, because when you start off with a word like square, then you're going to have to narrow it farther, and you're going to be out of luck. So you want to start with a big word like quadrilateral and then narrow it down. Okay. So go ahead. Quadrilateral that has what?
It's a quadrilateral that has two lines of symmetry through the midpoints of each of its opposite sides only, and it has two full.
Perfection.
Yeah, okay. I'll stop there.
Perfection. That's good. Okay. You get the idea, right? Okay. And there's more than one possible definition. So, when you study geometry, you don't always get that idea. When mathematicians look at these things, there's a choice of definitions, and they usually make, because a standard thing like E, are you familiar with E, the number E? I would think so.
Yep.
Yeah? So E has 500,000 properties. I mean, it's really an amazing number. What do you take for the definition? Well, in fact, there are like 5 choices. And if you choose choice A, then you can prove B, C, D, E. If you choose choice D, then you can prove A, B, C, and E. That's usually the way it works. So there's a choice of definition. Okay. Now properties. And so what I wanted to get at here was, I'm just going to do one of them because this is not so easy. But these properties are consequences of the preservation properties of the symmetries. All right? And the definition of the associated transformations. So let's do a kite. And I am going to use GeoGebra for this. So here's GeoGebra. I'm going to get a new window. There. And go here. And I don't know why this text effects thing is here. That's a glitch. Ignore that. So we said a kite had one line of symmetry that goes through. So I'm going to make a segment instead of, I think I can reflect across a segment. And we'll make it in the usual position. So here's a vertical segment. And then I'm still at the segment tool. And I'm going to make our kite according to the definition. And I'll really make it look like a kite. But we could rotate it if we want to. So that looks like a pretty good kind of kite. And now, or half of it, and now we're going to reflect. So we go to the reflection about a line. And let's see. Can I reflect several things? Or do I have to do one at a time? No, maybe I have to do one at a time. I know. Let's just take this point here. Do this again. Reflect this point around this line across. Yeah, there we go. And now I can take the segment and go from here to here, and from here to here. And now I'm going to do options advanced, because that shows me everything. If I go to the left-hand tool here, which says Object Properties, then I get to see everything. And what I want to do is label the points. So here's point A, B, C, and C prime. Those 4 points. I don't want to do that. I want them all to show. A, B, A. I thought if I did this, I would get every. Yeah, there we go. And I want to show just a name. I don't need a value. So hopefully that will show me. Yeah, I didn't get C prime. All right. Let's show the label here. Okay, so it's called C1. I'm not going to worry about changing the name. We're just going to. Oh, you know what? I am. I'm going to change this name to D. So rename it. Let's call that D. And this has got 2 names. I'm not crazy about. All right. Let's not worry about that. So A, B, C, D. That's not the usual way we label a kite, but we'll stick with it. We usually go around, right?
Mm-hmm.
Around the figure.
Yes.
Yeah, we all right. We can do that. We can rename. Let's make it good. So we'll. Not showing me a rename on this. Wait a second. There it is. Okay, so point C we're going to call point B. It may not like that. Oh yeah, and now it makes it B1. It's really clever. And then rename this to C. Whoever wrote this software is pretty, whoops. Try that. Better. Rename C. Okay. Yeah. Okay. So ignore this. And we have A, B, C, D. All right. And I'm going to draw the other diagonal. And I'm labeling it so that we can talk about it. Okay. So there's our kite. And we want some properties that follow either from the definition. And the definition was, you know what, I'm going to draw the line so that we can actually see. So here's the line of symmetry. I'll draw the whole line. So our definition was just that it has one line of symmetry. Okay? Mm-hmm. So I'm going to go back and forth between both of you, and I want you to name me a property. One property that follows either from the definition, either from preservation properties of transformations, in this case a reflection, so a preservation property of a reflection, or the definition of a kite, which was that it had one line of symmetry.
Okay.
Oh, wait a minute. I'm sorry. I need to label this point too. Okay. Go ahead.
There's 2 pairs of it has 2 pairs of sides that are adjacent to one another. Or the same lengths are.
Yeah, you use the letters. Use the letters for now.
AB or segment AB is congruent to 80.
Yes.
The length is due to reflection preserving lengths.
Good. So yes. So these 2 are equal, and similarly, BC is equal to
DC.
And then you were trying to say it in terms of the figure. So go back to that and see if you can.
What?
How are you going to say it without reference to the vertex labels?
Okay. The sides are just reflected.
So how could we describe AB and AD? They're what? How can we describe these things? What sorts of objects are they?
They're segments.
Yeah, but in terms of the figure,
Oh,
Their sides.
they're sides.
And-
They're sides. Yes, yes. And now we need a word that describes their position. How are they related to each other? And you mentioned this word when you were talking before.
oh,
Are they
Adjacent?
opposite? Yes, adjacent. Yes. So this is a what? This is a using all those words.
adjacent pair of
Yes,
sides.
a pair of yes.
Adjacent
so,
sides.
A pair of adjacent sides, right? And how are they related to each other?
They're the same length.
Yes. So this is a pair of equal adjacent sides or congruent adjacent sides. I like to use equal. Equal means the same length. I mean, everybody says that. So this is one pair of equal adjacent sides, and this is
A second pair.
a second pair. So a kite has two pairs of equal adjacent sides.
Okay.
Okay?
Mhm.
All right, Logan, give me another property.
AC is perpendicular to BD, or
Good. And now describe it in terms of the figure. What name applies to AC and BD?
diagonals.
Yes.
Yes.
Yes. So now can you make a sentence?
The diagonals of a kite are perpendicular to one another,
Good.
or
Bingo.
perpendicular.
Yeah, exactly. Good, good. You're what you're doing is coming up with a wonderful fact about writing that I didn't learn until I was teaching. Went through all college, all that kind of stuff, and I was teaching. And the Latin teacher, we would be trying to draft a memo, and he had all these words, and Mr. Sturch, that was his name, would always say, "Can't we? Do we need all those words? Can we make this shorter? Can't we make it more concise? Can't we?" And that's just the opposite of when you're writing an essay, right? It's I need 500 words, right? I need to put in more words. But good writing is not more words. Good writing is fewer words. Is saying it as concisely and clearly as you can. So, okay, that's my point. Okay, so we have two pairs of equal adjacent sides. We have perpendicular diagonals. Yes. Other properties. There's more.
Opposite angles are, what I should say is that
Use the letters first. First.
angle B and angle D are equal.
Yes. Yeah, that's right. The whole angle B and the whole angle D are equal to each other. Yes. Now think. So that's the first thing. Okay, what am I trying to say? Let's go slowly. Now, how do we say that? How do we talk about angle B and angle D with reference to the kite? They're what? How do we describe it? They're angles.
The non-bisected.
Okay. Let me ask a leading question. How do you describe side AB and side CD? They're what kind of sides? They're not adjacent. They're what?
No, which sides again? AB
and DC.
They're opposite.
Opposite, or opposite sides. Right. That's a hint. Angle B and angle D are
Opposite side or angles.
opposite angles, yes. So a kite has one pair of equal opposite angles.
Oh,
Yes.
Yeah.
Okay.
Yes. And right, just one pair. Good. Incidentally, when we're talking about angle A and angle B, we don't use the word adjacent for angles. We do for sides. These are adjacent sides, but we call them consecutive angles.
Okay.
They're not adjacent because they're not next to each other in that sense, but they're consecutive around the figure. Okay, so they're consecutive angles. There are words in math, okay, especially in geometry. All right, so one more property. Actually, there's two more properties that I can pick up. And they have to do with the diagonals. That's the hint. So we said the diagonals are perpendicular, but there's more.
AC bisects both its angles.
Yes.
Is that
Yes. Yeah. One of the diagonals bisects the opposite angles. That's right. So this angle here is equal to this angle here. Angle BAD equal to angle EAD. Okay. And then this angle down here. Good. One more. Is somebody coming in?
No, we're fine.
Yeah, 1 second. Sorry.
One more. And it also has to do with this diagonal. And it's not angles. This is a line of reflection. And what's the definition of line of reflection? So think of B being reflected onto D. Since B is reflected onto D, this reflection line is the what?
Line of symmetry?
Yeah, but yes. It's perpendicular, but it's more than perpendicular. It's more than perpendicular. It's not over here. Not over here. Just in terms of the letters, what two segments are equal that we haven't said?
BE and DE.
Yes, BE and DE are equal. Right. So this line is not only perpendicular, it's also the
bisector.
Yes, it's the perpendicular bisector. You remember our definition of reflection. Line of reflection is the perpendicular bisector of the segment joining the pre-image point to the image point. Good. Okay. Those are all the properties of a kite. And you get them all from those two things. Amazing. So the properties, the properties come from these transformational things. So our definition of a kite is no longer, the standard definition of a kite is two pair of equal adjacent sides. That's the standard definition. For us, it's not the definition, it's a property. Our definition is a kite is a quadrilateral with a line of symmetry going through two opposite vertices. That's our definition. Okay? So the definition is always going to involve symmetry. And then once we get the definition, all those properties just come out. We don't have to prove, way back when you took geometry, you had to prove triangles congruent. You had to go through all those proofs. We don't have to do that anymore. That's the advantage. Okay. All right. Let's go back to here. Okay, I'm not going to go through the rest because we're getting close to out of time. But I am going to say that number 5 is a quadrilateral hierarchy diagram. So that's a diagram that shows that quadrilaterals are special cases of others, like a tree diagram where you go down, and so like a square is not going to be on the bottom. That's a special case of lots of things. All right. And there are new kinds of situations. There's new inclusions here because of our symmetry definition. So I'll just say that for us, a rectangle is a special isosceles trapezoid, right? Because it has one line of symmetry going through two opposite sides. The standard definition of a trapezoid is not that. So this has more inclusions. Yeah.
Last night I was doing this diagram, and I started to base it off of how many lines of symmetry each one has. And I started off with multiple different. I tried to do different diagrams, and I kept on getting a little confused because I kept on separating the kite into different tree altogether with nothing underneath it. Should I go back and put that into tree?
Yeah, there's more inclusion. There are more inclusions, yes, than you would think.
Okay.
Yes, there are lots of special kites. Yes.
All right, great.
Good. All right. We're not going to do, let's see, just 1 through 5. Yeah. Well, I think that's what I said in the homework. Yeah, review 1 through 5. That's it. So that's what you have. We're not going to do 6 until after the test. So I want you to go back and revise. That's your homework. Okay?
Okay.
That's the main part of your homework. The only other thing I want to do in the remaining 4 minutes, I want to close this, is just ask if there are any questions about these other things. So this is the, and I was going to do the SAS similarity proof, but we'll have to put that off. But the similarity proofs are a lot easier than the congruence proofs because we have the congruence facts now. So did you understand this SSS similarity proof?
Yeah.
Right. We blow it up and then we know the sides are equal, so we know side congruence. Good. And the other ones are similar.
Okay.
The word similar in English, right? It's difficult. are about the same, but the mathematical word similar is different from the. Okay. I had this. All right. This cases business. That's a long discussion. So I think we have to put that off. So I'm not going to do that now. And the did you understand this HL congruence thing that we had talked about this. And I wrote it up, tried to write it up carefully. So the idea is that, yeah, okay. So I hope that makes sense to you. And then this is the test preparation sheet that I posted for you. And this has the instructions. These are the same instructions. So I really tried to tell you what was going on here. So this is what you'll need to do. So this question will ask you to describe one isometry or one dilation, something like that. And you'll need complete definitions. So, so review that. You won't need to define a vector. That's too complicated. And so here's an example. Example of a question. Question will look something like this. So you'll need to know your definitions. So review that definition sheet. Then there'll be some stuff about, completing this. So graph paper would be helpful. So you can, make some examples just to write on. Then there'll be, we talked about this today, composition of reflections into a single equivalent isometry. We talked about 2 reflections, or maybe something with 3, so you have to look at that. And this is 5 and 6 are similar. And then there'll be the table, the preservation properties table. You had done that, so look that over. What's preserved? There'll be an informal proof kind of question. It begins with the word explain. A diagram will be given that you'll need to add to. Okay, you can either do that in the document or write your answer scan, or you can insert it, or you can do it separately and scan it and send it separately. It doesn't matter. And then there'll be a final challenging problem asking you to make a GeoGebra sketch and list the properties of a figure. Okay.
Okay.
So that's it. That's exactly what it's going to be.
Okay.
All right. It is the hour. The hour is up. I'm happy. I'm available if you want to have a session with me. You want to talk. You want to do anything. Let me know. Give me 2 or 3 times. 2 times. I'll probably be available one of them. And I'm happy to spend time with you, either together, both of you, or separately. Up to you. Okay? All right.
Oh, I have one question about the diagram. Will it be more of a web, than a hierarchy?
Oh,
like you'll have once you get away from the quadrilateral, it'll be more of a web underneath, right?
Yes. It does look like a web, and in fact, it's called a web diagram sometimes. Yes.
All right. Thank you.
Good. All right. Don't want to take up more of your time. Have a great rest of your week, guys, and we'll see you on Friday.
You too.
You too.
Bye.
Bye.